Hello, everyone. Thank you for the introduction. Yes, I am going to present our study on the indoor environment and the use of windows in French dwelling monitored during the summer with heatwaves. My name is Mathilde Hostein. I am a PhD student at Cerema and ENTPE in France. I work on the impact of climate change on thermal comfort by taking into account the occupant behavior and the urban context. I am supervised by Bassam Moujaled and Marjorie Musi at Cerema and Mohamed Elmankibi at ENTPE. So let me start by explaining why we're working on window state modeling. The presence and actions of occupants have a major impact on the indoor environment, especially in their homes where they are more free. And in addition, in France, the majority of households are not yet equipped with air conditioning units. So the use of windows is one of the main passive cooling strategies. And as we work on summer comfort, we first ask ourselves how we could realistically model occupant behavior. And so to do this, we adopted an approach based on in situ measurement. So I'm going to present the results of the analysis of the data collected during the summer of 2022. I will first present the field measurement campaign, then the window patterns observed during summer, and finally the window state models trained on the data collected. So let's begin with the field measurement campaign. So data was collected as part of the creative project, which focuses on thermal comfort and indoor air quality in residential buildings during heat waves. A field measurement campaign was conducted in 2 French cities of the same region in the southeast of France from June 13 to September 27. 4 dwellings were monitored, including 1 house and 3 apartments in the same multi-family building. 3 types of surveys were filled in with the occupants. So the logbook was filled in by the occupants independently during a 1-week period of heat waves during the summer. The thermal comfort surveys were completed by the occupant independently through the summer. And the general questionnaire was filled in with the occupants when the sensors were removed. It focused on the use of windows and shutters and the comfort perception during summer and heat waves. So regarding the measurements carried out in each dwelling, so here is an example of the instrumentation plan for dwelling A. Oboe recorders measure temperature and humidity in the living room, master bedroom, kitchen, bathroom, and loggia. Pollutants, including CO2, light VOC, and fine particles, are measured only in the living room and the master bedroom by NEMO sensors. Temperature, humidity, light VOC, and fine particles are also measured outdoors at each site. Here we can see the NEMO outdoor sensor powered by a solar panel. And also wind speed and direction, as well as solar radiation, were collected from a nearby weather station. And last but not least, we use contact sensors which records the openings and closings of the windows. So these sensors only record the moments when the window opens or closes, but the percentage of opening is unknown. Then, once the data has been processed, we can start plotting graphs to check whether the patterns observed are similar to the occupant statements in the surveys. So, based on surveys, thermal environment is perceived to be extremely hot during heatwave days in all apartments in Lyon. So we can see that the temperature is much higher there than in dwelling D, which is a single family house in Clermont-Ferrand. And its occupants are also particularly active in the passive lowering of temperature. However, even in dwelling D, occupants consider the thermal environment unacceptable during heat waves and especially at night. Here is a figure to show the link between the indoor environment and the window openings in the living room of dwelling B, with a focus on the third heat wave. So temporal evolution of temperature is shown as a solid line. CO2 levels are shown as a dotted line. And the periods in blue are when the window is open. And also at the bottom, we have added the time when the air conditioning is on in orange and the fan in green, as this dwelling is equipped with this system. So we can see that there are many window openings in the evening. In the morning, there are often openings lasting about an hour with the fan on. The fan and air conditioner are switched on in the afternoon when the occupants are present. And during the night, the air conditioner is switched off and the fan changes room. And here is the same figure, but for the living room of the last dwelling. And you can see straight away that the behaviors are very different. So this dwelling is not equipped with air conditioning, so instead we plotted the periods when the shutters are open in orange below, and green is always the fan. We can see that windows and shutters at the same time are open for much longer periods. Every morning and even some evening. And the fan is much less frequently switched on, being off 96% of the time. And as we can see that occupants seem to open windows only at certain time of days, we plot a figure showing the time of day when an opening is recorded in blue and a closing in orange. So this trend is particularly pronounced for the two dwelling B and D, on which I focused just before. So this is what we observed. And finally, we look at modeling the states of windows using the data collected in this field measurement campaign. So the aim is to use machine learning to predict the window states in order to integrate realistic occupant behavior into building performance simulation. So the data collected must first be formatted to be able to train models. So to do this, we create a table in which each row corresponds to a window state with a 5-minute time step. And explanatory variables are associated with each window state. So they are environmental variables measured indoors or outdoors, and contextual variables such as the room, the day of the week, or the time of day. So not all of these variables are available for all windows. So we train 6 different models with different input data. So yeah, we don't always have information on all these variables, and so it's useful to see whether a model trained just with contextual variables and outdoor temperature performs well, for example. Next, we use Python scikit-learn library to compare 4 types of data-driven models: a decision tree, a random forest, gradient boosted tree, and artificial neural networks. The results show accuracy above 85% and good FM score, but a little lower. So here are the details of the 2 metrics for the 4 types of models shown here with a different color. And on the left, the models are trained with all explanatory variables. And on the right, the models are trained with contextual variables and outdoor temperature and humidity only. So the 4 types of models trained on our data can be considered as performant. Accuracy is always higher than 85%, and it does not seem to be affected by the loss of information, meaning explanatory variable, unlike the FM score, which fall little. Neural networks are the best performing of the 4 model types. They maintain a good FM score, which does not fall below 78%. And it is interesting to notice that performant window state models can be trained with only contextual and outdoor environmental data. Because it's not always possible to monitor inside dwelling. To give you a better visual idea, here's an example for 1 week in the master bedroom of dwelling C, using the model with the fewest input variable. So this figure compares the 4 types of model with the window state observed. So we can see that the models capture behavioral trends, even though they have only been trained with contextual and outdoor hygrothermal variables as inputs. But there are also times where there are little closing or little opening. It cannot predict. This is an example for 1 room and 1 week to allow us to visualize the type of output that the 4 types of model can give us. And the next step is to provide these models as input to building performance simulation to compare indoor environments, which is the information we are ultimately interested in. And so finally, what are the next steps? So the metrics were calculated on the same dataset, separating it into a training dataset and a validation set at 80-20%. And this is a classic approach to model performance evaluation. But the next step is to test the trained models on a new dataset. And so to this end, we implemented the same methodology for a field measurement campaign last summer in a residential building in Nantes, which is another French city. And so this will enable us to assess the generalizability of our model. And finally, let's talk a little about the CG's limitation. We only measured variables related to thermal comfort and indoor air quality. And we added contextual explanatory variables as habit seems to be very important in the use of windows. However, when interviewed, occupants declared that they open windows to ventilate out of habit and to evacuate it. Yes, so we measured that. But sometimes the occupants are forced to close them for fear of intrusion, outside noise, drought, or dust. And we were unable to include this explanatory variable, which is a limitation of the study. And that's why we conducted 8 semi-structure interviews with households in Lyon last summer in order to consider occupant behavior in a more holistic way. And the aim will be to build an agent-based model to compare with these data-driven models. So this presentation is based on the paper presented at the last AIVC conference. So here's the reference if you want more details. But the modeling part is composed of new results, which will be published soon. So thank you. And now is question time.